Okay, guys, so here we've got question 1 of this paper. This is a completing the square question, hopefully nice and easy start to the paper. So if we're going to complete the square here, what we've got to do is first we've got to factorize out the 5 from the x squared term. So we're going to get 5, big bracket, x squared minus 14 upon 5x plus 8, right? We don't have to bother with the final constant term. And then if we want to complete the square, what we do is we look at the coefficient of the x, which in this case is minus 14 upon 5. We've got to half it to get minus 7 upon 5. Then what do we do with that, minus 7 upon 5? Well, we write like this, x minus 7 upon 5 all squared minus the minus 7 upon 5 squared. Okay, so I'm hoping that that should be something that's fairly familiar to you now if you're sitting add math, right? What you do to complete the square is you take this number here, you halve it, you stick it here, and you square it, subtract it off. Okay, so I think now we just want to simplify all of this. So we're going to get 5 bracket x minus 7 upon 5 all squared. And that's going to be minus 5 times by negative 7 upon 5 squared, which is going to be 49 upon 25 plus 8. Now, hopefully we can see this is going to simplify because we can divide top and bottom of that fraction by 5. So that will cancel. We give 5. And we can rewrite 8 in terms of fifths. So instead of 8, we can write this as 40 upon 5. And if we've got minus 40 upon 5, if we've got minus 49 upon 5 plus 40 upon 5, that's minus 9 upon 5. I can rewrite this thing here. It's 5 bracket x minus 7 fifths all squared minus 9 fifths. Now, what does this mean? We want to write down for part B, the stationary point on the curve. Well, hopefully one of the things you also will have learnt by now is if we've got k bracket x minus a squared plus b, then the coordinates of the stationary point will be a comma b, right? So in other words, you take this value here as your x coordinate and this value here as your y coordinate. So in this case here, we've got 7 fifths, okay, is our x coordinate. And our y coordinate would be minus 9 fifths. Now, I think often the mistake that people make is they get the negative sign the wrong, right? They forget that this needs to be x minus a, and this is a positive b, okay? I get that. One of the ways you can think about what's happening here is this is a quadratic equation where the graph has been shifted to the right by 7 upon 5, right? So the x coordinate moves to 7 upon 5, and it's been shifted down by 9 fifths, right? It's minus 9 fifths that takes us to there, okay? Okay, then next part of question 1, we've got part C. We want to sketch the graph of the modulus of 5x squared minus 14x plus 8. And we want to state the coordinates where the graph meets the coordinate axis. Now, I think it's always best thing whenever you're asked to sketch a modulus graph to just sketch the ordinary graph first. So we're going to sketch y equals 5x squared minus 14x plus 8. And if we want to find the x-intercepts of this graph, it's the same as asking where y is equal to 0. So we're going to solve 0 equals 5x squared minus 14x plus 8. And so I think we're probably going to try to factorize this. So we're going to get 5x and x. Now, what are we looking for here? We're looking for two numbers. They're going to multiply together to give 8. And they've got to combine in some way that we're going to get negative 14 here. Well, we know, therefore, that both the numbers have got to be negative, right? Because there's a negative here. And so what are we going to look for? I think probably negative 2 and negative 4. So the negative 2 will go there. The negative 4 is going to go there. Why do I think that? Well, because 5x times by negative 2 is minus 10x. Negative 4 times by x is minus 4x. So minus 10x minus 4x is minus 14x, which is what we want. So we have got x-intercepts at x is equal to 4 fifths and x is equal to 2. And it may be helpful later on, I suspect, to write that as 10 fifths. Okay? Those are our two x-intercepts. Where is our y-intercept? Well, y-intercept is when x is equal to 0. And that should be fairly straightforward. That's where y is equal to 8. Okay, now we've probably got enough information, I think, to sketch this now. So we're going to sketch our quadratic. So let's try to draw on a set of axes. So we're going to have an axis like that, axis like that, I guess. And we're going to deal with everything in terms of fifths. So let's say that's 1/5, 2/5, 3/5, 4, 5, 6, 7, 8, 9, 10. We know that we're going to cross the axis at 4/5, which is there, and 10/5, so 5, 6, 7, 8, 9, 10. We learned in the previous question that the vertex is going to be at 7/5, is there, exactly between our two roots, and minus, was it minus 9/5, I think was the answer. Let me just go back and check. Minus 9/5. Yeah. Okay, and our y-intercept is going to be here at 8. Now, I know it's not to scale. It doesn't really matter as long as I've indicated a point. So the points are, it crosses the y-axis there, crosses the x-axis here and here. It's going to have a vertex, let's say, there. So let's try to draw that. I think probably my graph is going to be a bit ugly. I do apologize for that in advance. Our graph is going to look like, I try to get that looking sort of nice, I hope. It's a bit difficult on a tablet, guys. I hope you appreciate that. Okay, something like that. Something like that. It's good enough, good enough. And so now we've got to ask ourselves the question, well, what's this going to look like if we apply a modulus to it? Well, if we apply a modulus, the modulus, all it does, it takes negative values and makes them positive, and positive values remain the same. So these here are positive values of y there and there. So that's going to be unaffected by the modulus. The modulus is still going to keep those guys the same. Okay. But these values here, this is where the modulus is going to turn them into positives. So the modulus is going to do kind of like that to them. Oh, that's not very good. Try that again. A bit better. Okay. And so what will this coordinate here be? That coordinate now will be 7/5, comma, positive 9/5, because the y coordinate has been reflected in the x-axis. Okay, I hope that was helpful. Okay, last part of this particular question, we've got to write down the range of values of k for which this equation, the modulus graph equals k, has 4 distinct roots. Well, what we've got to do is we've got to imagine the graph of y equals k, where k is just any constant. And that's going to look like a straight line. So I'm going to draw a straight line here. I will draw it in yellow. So here's a straight line. And so the number of solutions to this is going to be found by the number of intersection points between the graph and the curve. Do you beg your pardon? I was a bit lazy earlier. I should have got rid of the ordinary quadratic. Let me just get rid of that. Otherwise, it's going to be a bit confusing. So that's gone. Okay. So what you want to do is you want to count the number of intersections between the line and the curve. Well, here we've got 1 intersection, 2 intersection, 3 intersections, 4 intersections. So that looks pretty good. Well, let's consider some of the other cases. Let's say I was to move that line down to here. Well, here there are going to be no intersections, right? Because we're below the x-axis. What about here? We're here. If we're on the x-axis, there are going to be 2 intersections, which is we're going to be our x-intercepts there and there. So that's 2 intersections. What about if we were here? Okay, so let's say we had this thing. Okay, so we're just touching the vertex point there. Well, in that particular case, we're going to have 3 intersections. 1, 2, 3. And now let's imagine that we're above the vertex. So let's say we are now here. And we're going to have 2 intersections. Okay, 1 intersection here, and another intersection here. So basically, what I'm trying to say is if you've got k less than the x-axis, then you're going to have no intersections. If you're on the x-axis, you're going to have 2 intersections. If you're between the x-axis and this vertex, you're going to have 4, right? 1, 2, 3, 4. If your line is just touching the vertex, you're going to have 3. And if you're above the vertex, you're going to have 2 intersections. So really the key thing is that our value of k needs to be greater than 0, because it's got to be above the x-axis, and it's got to be less than the value of our vertex, which is 9/5. Okay, and that's going to be the condition for having 4 roots. Okay, so this is question 2. We're given a polynomial p with integers a, b, and c that are yet unknown. And in part A, we're told that p double prime of a half is equal to 32. We want to show that a is equal to 6. Well, what does this really mean? It means that if we differentiate the polynomial twice and substitute in a half, we should get 32. So let's take our polynomial and differentiate it once. If we do that, we're going to get 3ax squared plus 14x plus b. We differentiate it again, so p double prime. We're going to get 6ax plus 14. And what we're saying is if we substitute in a half into that, we should get 32. So I substitute in a half. I'm going to get 6a times by a half plus 14. That's going to be 3a plus 14. Okay, and therefore we're saying that 3a plus 14 must be equal to 32. So 3a will equal to 18, and a will equal to 6. Okay, so that's part A of this question done, hopefully quite simple. Part B, we're given that p of x has a factor of 3x minus 4 and a remainder of 7 when divided by x plus 1. Well, we've got two statements here, right? The factor is 3x minus 4, and this statement here about a remainder when we divide by x plus 1. Let's deal with the first statement. Firstly, if we have a factor of 3x minus 4, we can find the corresponding root by setting that equal to 0. We rearrange, what we're going to get is x is equal to 4/3, and so therefore this is a root. Now, what does a root mean? It means that if we substitute that value into the polynomial, what we should get is 0. Okay, so that's really the first statement, statement 1, very important. The second statement is that we will get a remainder of 7 when we divide by x plus 1. If we, that means that if we substitute x is -1 into the polynomial, then what we should get is 7. Okay, so we've got two statements here. Statement 1, statement 2. And what we've got to do is just got to follow through each statement. So we're going to substitute in 4/3 into the polynomial and set the polynomial to 0. And then we're going to substitute -1 into the polynomial and set that equal to 7. So let's try to do that. So we've got our polynomial is ax cubed plus 7x squared plus bx plus c. Okay, and of course we found out in part A that a is equal to 6, so we can replace that there with a 6. Okay, so we're going to substitute in 4/3. That means here we're going to get 6 times by 4/3 cubed. Well, that will be 64 upon 27. Plus 7 4/3 squared, that will be 16 upon 9. Plus b times by 4/3 plus c. Okay, and what we're saying is, well, that thing is equal to 0. So 0 is equal to 6 times by 64 upon 27. Well, we can cancel off by dividing top and bottom by 3. So we're going to get 2 times by 64 over 9 plus 7 times by 16 upon 9 plus b times by 4 upon 3 plus c. Now, the fractions are the thing that make this a bit annoying, isn't it, right? So the way we're going to deal with the fractions is we're going to multiply the whole equation through by 9. That's going to get rid of our fractions. So if we do that, we'll get 0 is equal to 2 times by 164, which is 128, plus 7 times by 16. Well, 7 times by 10 is 70. 7 times by 6 is 42. So if I add those up, I get 112. If I've got 4b upon 3 and I times it by 9, and what I'm doing is I'm going to multiply the numerator by 3, so I get 12b there. And here, I've got to remember I've got to multiply the c by 9 as well. Okay, well, I think I can simplify this. 128 plus 112, that is going to be 240 plus 12b plus 9c. And it looks like I can divide everything through by 3. So I'm going to get 4b plus 3c is equal to minus 80. Okay, and that's going to be an important equation there. The second thing I've got to do now is I've got to substitute in -1 into my polynomial. So I've got to do this thing, get the second equation. So what am I going to get? So e of -1 is going to equal 6 times by -1 cubed, which is just -1, plus 7 times by -1 squared, which is +1, plus b times by -1 plus c. And we know that this thing must be equal to 7. Okay, so this has got to be equal to 7. We substitute that in, down. So 7 will equal to -6 plus 7 minus b plus c. So 7 will equal to will equal to 1, beg your pardon, minus b plus c. And so we could say that 6 is equal to minus b plus c. Okay, now the key thing is here what we've got is we've now got two equations. So I'll label this as 3 and 4. Okay, and what we want to do is we want to solve simultaneous equations with those two. Well, I think probably the simplest way to do this is actually to do substitution. So I'm going to rearrange equation 4. If I do that, what I'm going to get is c is equal to 6 plus b. And I'm going to substitute that into equation 3. I substitute into 3. Notice I'm always writing down what I'm doing, right? It helps the examiner to see your method, but it also means if you make a mistake later on, it's quite easy for you to go back and correct your work. So I encourage you to do that. Okay, so if I substitute in, I get 4b plus 3 times by 6 plus b is equal to -80. Okay, and so rearranging this, I get 4b plus 18 plus 3b is equal to -80. And so 7b is going to equal to minus 98. And is that going to be divisible? I think it probably will be. If I take b and divide it by 98, what will I get? Well, 70 divided by 7 is 10. I've got a remainder of 28. 28 divided by 7 to 4. So b will equal -14. Okay? And then I can just substitute back into here, right? So c would equal to 6 plus -14. And 6 plus -14 is -8. Okay, let's go back and check the question again, make sure that we've answered it. Want to find the values of b and c? Yeah, we found the values of b and c. Okay. Okay, so we're now in part C of this question. We are to write p of x in the form 3x minus 4 times by q of x, where q is a quadratic factor. Now, from the previous parts of the question, we learned that p of x is this polynomial here, and the easiest thing to do now is to divide that through by 3x minus 4. So we're going to divide this whole thing through by 3x minus 4. And the way we do that, if you're not too sure, is as follows. This thing here, the 6x cubed, is what we call our leading term. We divide that through by 3x. If we do that, we're going to get 2x squared. We then take that 2x squared and we multiply it by the 3x minus 4. We do that, then we're going to get 6x cubed minus 8x squared. And we're going to subtract this thing off. Now, if we do that, 6x cubed minus 6x cubed is 0. And we're going to get 7x squared minus 8x squared. Well, minus is a plus, so that's going to be 15x squared minus 14x minus 8. Okay? This thing here, the 15x squared, is now our new leading term, so we divide that by 3x. 15x squared divided by 3x is 5x. We get here 5x like that. And so if we were to take that 5x now and multiply it by the 3x minus 4, we get 15x squared minus 20x. And again, we're going to subtract off. 15x squared minus 15x squared is 0. And minus 14x minus 20x is 6x. And so 6x is our new leading term. We're going to divide that by 3x minus 4. Divide it by 3x, beg your pardon, which gives us 2, right? 6x divided by 3x is 2. We take that 2, we multiply it by the 3x minus 4, give us 6x minus 8. Again, if we subtract that off, we get 0, which is what we should expect. Now, if this is the case, this means that we can now write our polynomial p of x as being equal to 3x minus 4 times by 2x squared plus 5x plus 2. Okay? And I think we can probably also then, for the next step, the next question, we can factorize this even further. We get 3x minus 4. If we factorize that quadratic, we're probably going to get 2x here and an x term here. And then we want two numbers that are going to multiply together to give positive 2. And we've got to choose those numbers in such a way that we're going to get 5x here. While it seems to me that if we've got plus 2 here and a plus 1 there, that would work. The reason for that is we're going to get a 2x times by 2, which is 4x, and a 1 times by x, which is 1x, and 4x plus 1x is 5x, which is what we want. And of course, 1 times by 2 is 2. So here what we've done is we've now written p of x in terms of its linear factors. And if we wanted to go one stage further, if the question asked, we could therefore state that the roots would be x is equal to 4 upon 3, x is equal to minus a half, and x is equal to negative 2. Okay? Okay, so we're now in question 3. We've got the points A and B with coordinates 2, 5, and 10, negative 15. And we're told the point P lies on the perpendicular bisector of AB, that the y-coordinate of P is negative 9. We want to find the x-coordinate. Now, ordinarily with these kind of questions, I would say the best thing to do is always to sketch it out. And I think that's probably what I'm going to do in this case anyway, even though it may be a little bit redundant. Sketch doesn't have to be super accurate, but it should be clear and able to help you. So let me try to do that like this. Okay, so let's say that we've got the coordinate of A here, 2, 5, and then let's make that. So A is the coordinate 2, 5. And we've got B is the coordinate 10, negative 15. So I don't know, maybe we draw that like that. So B is 10, negative 15. Okay, well, we want to draw the perpendicular bisector of AB. Well, probably the best thing then to do is to actually draw the line AB. The line AB kind of goes through like that. And the perpendicular bisector is the line that goes through the midpoint of AB. So it's going to go through this point here, the midpoint, M. And it's got to run perpendicular to it. So this line here, let's say, like that. Okay, perpendicular. All right, so if we're going to do this, what we need to do is we need to find the equation of the perpendicular bisector, which means we need to find the coordinate of the midpoint, and we need to find the gradient of the line AB. So midpoint is found by adding up the two x coordinates and dividing by 2. So 2 plus 10 divided by 2. Like that. And we've got to add up the two y coordinates and divide by 2 to get the y coordinates. So 5 plus minus 15 divided by 2. And so if we get that, we're going to get 6 and minus 5. Okay, so the coordinate of our midpoint is 6 minus 5. Okay, then, well, we next want to find out the gradient of the line AB. So the gradient of AB. And the gradient of AB is y2 minus y1, so minus 15 minus 5 over x2 minus x1, which is 10 minus 2, right? So x2 minus x1. And minus 15 minus 5 is minus 20, and 10 minus 2 is 8. We get minus 20 upon 8, or we can divide that through by 4, which gives us minus 5 upon 2, beg your pardon. Okay, Now then, that gives us the gradient of the blue line, AB, but we want the gradient perpendicular to that. And we should know that if two gradients are perpendicular, then the product of those gradients is equal to -1, right? So m1, m2 is equal to -1. That means that the gradient perpendicular to AB, in this case, is going to be -1 divided by -5/2, and that's 2/5. Okay, so we know that the gradient of our perpendicular bisector is 2/5, and we know that the coordinate point that it goes through is 6, -5. So that means that we can use y minus y1 is equal to mx minus x1 to find the actual equation of that bisector. So we're going to get y minus -5, y minus -5 is +5, is equal to m, which is 2/5, x minus x1, where x1 is 6. Okay, now then, if we just return back to our question, we want to find the coordinate of p. Now we're told that the y coordinate of p is -9. So p is probably going to be somewhere here, I think, isn't it? Something like that. And so we just substitute -9 for our y coordinate into here. We say when y is equal to -9, we're going to get -9 plus 5 is equal to 2/5 x minus 6. And so that's going to give us here -4 is equal to 2/5 x minus 6. Okay, and multiply both sides by 5 and then divide by 2 is going to give me -10 here. It's equal to x minus 6. And so x is going to equal to -4. And so that would be the x coordinate of my perpendicular bisector. Now, obviously here, it doesn't correspond on my diagram because my diagram wasn't super accurate, but it may well help me in the next part of the question. Okay, so here is part B. We're told that the point R is a reflection of P in the line AB. We want to find the coordinates of R. Now, I think the most important thing about this question is to notice that it is only worth 2 marks, which means that it can't be so complicated. Now, I think quite a few people will try to use the formula for the length of the line or that kind of stuff. It's a bit unnecessary if you just think about it. So let's just go back to our diagram. Right, here's our point P. Okay, this is the point P, which we said has got x coordinate -4 and y coordinate -9. I know it's not accurate according to the axis, but it doesn't matter in this case. Okay, now if the point R is going to be the reflection in the line AB, then R is going to be somewhere roughly there, and that means that this distance here from P to M has got to be the same as this distance here from M to R. But another way of thinking about that is to say that if I move a little distance to the right from here to here, and a little distance up, then I'd have to move the same little distance to the right and the same little distance up there. So really what we've got to ask is, well, what's this distance here? This distance that takes me from -4 to 6 is a distance of 10. So that's a distance of 10. And what's this distance that takes me from -9 all the way up to -5? That distance is 4. In other words, to go from P to M, I go 10 to the right and I go 4 up. But to go from M to R, I've also got to go 10 to the right and I've got to go 4 up. In other words, I've got to add 10 to my x coordinate, will make that 16, and I've got to add 4 to my y coordinate, which will make it -1. What I'm saying is R will be the coordinate 16, comma, -1. Okay, I think again, this is a case where a diagram which is clear, doesn't have to be accurate, but it has to be clear, will really help you to get the answer. Okay, so this is question 4. We're given a velocity time diagram, which has got maximum velocity here of v, and we're told that the particle travels a distance of 800 meters in the full 45 seconds. What we want to do is we want to try to find v. Okay, well, the key fact that we need to use here is that the area under the graph is equal to the displacement, right? Or in this case, the distance traveled. So what we want to do is we want to find the area under this graph and set it equal to 800. Now the thing is, this graph is made up of several different shapes, so it's probably a good idea to split them up. Here we've got one shape, which is a triangle. Okay, we'll call that area 1. Another shape here, which is a rectangle. And we've got another shape here, which is going to be a trapezium, like that. And we've got another shape at the end, which is just a triangle. Okay, I'll call them areas 1, 2, 3, and 4. And I'm just going to find them all separately, I think. So area 1, which is my blue triangle, is equal to a half base times height. So that's a half 10 times by 10, which is going to be equal to 50. So that's fairly straightforward. Okay, let's find area 2, which is just the area of the rectangle. Well, area of a rectangle is base times by height, which is 10 times by 10. And so that's equal to 100. Okay, area 3, a little bit more complicated, the area of a trapezium. Area of a trapezium is a half of this length plus this length times by that width. So it's going to be a half of 10 plus v times by the width, which is 10. Okay, and it's probably a good idea to simplify that. So a half times by 10 is going to be 5. And then we're going to have 5 times by 10 plus v, which would be 50 plus 5v. Okay. All right, then we'll do area 4, which is our white triangle. So our white triangle is going to be a half base times height. There's a half. The base is 15. And the height is v. All right, so we're going to have 15v upon 2. Okay, well then the key thing is really to add all these up and say that they are equal to 800. So if I add them up, I'm going to get 50 plus 100 plus 50 plus 5v plus 15 upon 2v is equal to 800. We just try to make sure we avoid mistakes, right? So here what we're going to get is 50 plus 100 plus 50 is 200. We can subtract that from both sides, which means we're going to get 600 is equal to 5v plus 15v upon 2. And we can combine these two fractions here. So it's going to be 10v upon 2 plus 15v upon 2 is 25v upon 2. You get 25v upon 2 is equal to 600. And so 25v is equal to 1200. Okay, and then we want to divide both sides through by 25. Well, there are 4 25s in 100, right? And I've got 1200, so it's going to be 12 times by 4, which is 48. Of course, you've got a calculator, but it's good to be able to do some mental math as well. Okay, so the velocity there is 48. Okay, so here is part B. We want to find the acceleration of the particle when t is equal to 35. Okay, well, the key thing to know is that for a velocity time diagram, the acceleration is going to be given by the gradient. So we just got to go up a little bit, got to find where t is equal to 35, or t equals 35 is going to be somewhere here. What we're really being asked to do is we want to find the gradient of that line there. Okay, so I'll just do this up here, I think. So the gradient of that line is going to be y2 minus y1. So the y2 is 0, the y1 is v, we know is 48. We get 0 minus 48 over x2 minus x1. So our x2 is going to be 45, and our x1 is going to be 30. We get 45 minus 30, which gives us 48, or minus 48, beg your pardon, over 15. We can divide through by 3. If we divide negative 48 by 3, we get minus 16, beg your pardon. And 15 divided by 3 is 5. Sorry about that, beg your pardon. Okay, and so that's going to be our answer, negative 16 upon 5. Right, so here we have question 5. We're told about a triangle, which has got lengths AB, BC, and an angle ABC equal to 120. What we want to find is we want to find the length AC. Now, I've drawn a diagram here. I think the key thing to understanding this diagram is that the angle ABC here must be obtuse. It's 120. And we want to label things very, very clearly. How are we going to do this question? Well, we need to use the cosine rule. Cosine rule, if you've forgotten, is a squared is equal to b squared plus c squared minus 2bc cosine a. And in this particular case, this is our a squared is equal to b squared plus c squared minus 2bc times by the cosine of a, which is that angle there. All right, so now what we've got to do is just got to really substitute in. So this is going to be 5 root 3 minus 6 all squared plus 5 root 3 plus 6 all squared minus 2 lots of 5 root 3 plus 6, or 5 root 3 minus 6, beg your pardon, minus 6 times by 5 root 3 plus 6 times by the cosine of 120. Okay, now what we've got to do is just got to expand this, right? So we're going to start with the first bracket. So if we expand this bracket, we're going to get 5 root 3 squared. If we do that, 5 squared is 25, root 3 squared is just 3, so we get 25 times by 3. And we're going to get 5 root 3 times by minus 6, which is minus 30 root 3, but we're going to have 2 of those, that's minus 60 root 3. Then we're going to get minus 6 squared is positive 36. Okay, well then the next bracket is basically the same thing. We're going to get 25 times by 3. But this time we're going to get plus 60 root 3 instead of negative. And we're going to get plus 36 again. All right, let's expand this bracket here. So we're going to get minus 2 times by, well, 5 root 3 times by 5 root 3, as we said before, is 25 times by 3. And notice what's going to happen next. We're going to get 5 root 3 times by 6, which is plus 30 root 3. Then minus 6 times by 5 root 3, which is minus 30 root 3. So those two things are going to cancel off. And we're left with minus 6 times by positive 6, which is minus 36. There we've got minus 36 times by cosine 120. And we're told in the question that cosine 120 is minus a half. Right, so we can go over here. We say that that thing there is minus a half. Now all we've got to do is really just got to simplify all of this, just tidy it up. Okay, so firstly, we're going to have 25 times by 3 is 75. Now, the 60 root 3 and the minus 60 root 3, they're going to cancel each other off. So that's gone, that's gone. We have got then 36 plus another 75 plus another 36. And here we can say, well, the minus 2 and the minus a half, they cancel each other off. So what we're left is plus 25 times by 3, which is 75, minus 36. Okay, we're not really supposed to use a calculator according to the question, so why don't we try to do this in our heads? Firstly, we can get rid of one of the 36s because we've got 36 minus 36. Okay, and then we're going to get 3 lots of 75. Well, it's kind of up to you how you want to do that. You can say 3 times by 70 is 210. Okay, and then 3 times by 5 is 15, so that would be 225 plus 36. And then 225 plus 36. Well, if you add 30, you're going to get 255. And you add 6, you're going to get 261. And the danger is you're going to forget that this is a squared, and you need to square root. So you've got to square root this, the 261. Okay, well, that's going to involve you trying to simplify that surd. Well, if you add up those digits, right, you see that they are going to be a multiple of 3, which means that this thing is going to be divisible by 3. So you want to kind of think your way through that. How's that going to be divisible by 3? Well, 240 we know is divisible by 3. It will give us 80. And that's going to have a remainder of 21, and 21 divided by 3 is 27. So we could say that this is 7, beg your pardon. So we could say that this thing is equal to 3 times by 87. And we should also notice, I think, that 87 will be divisible by 3 as well. Because if you think about it, it's quite close to 90, which would be 30 times by 3. And so this will be 29 times by 3. So what we've got here is the square root of 3 times by 3 times by 29, which is 3 squared times by 29. So if we simplify that, we're going to get 3 root 29. Okay, now with the last couple of steps, probably what you'll do is you just use the calculator. But again, the question says you're not supposed to use the calculator. So I think it is important that you try to explain what you've done here. Okay. Then, so now we're in part B of this question. We've got another triangle, which is PQR. And we're told that the angle PQR is 30 degrees. So this time we're dealing with a acute angle. And we're told the length of PQ is 3 plus 2 root 5. And we're told the area of the triangle is 2 plus 5 root 5 upon 4. Now notice that what I've done is I've drawn a diagram here, and I strongly encourage you always to draw diagrams. I think it makes it easier for you to comprehend the question. Now, in the previous part A, we had to use the cosine rule, and in this, we're going to have to use the area formula, which is the area of a triangle is equal to half BC sine A. So for this particular triangle, we're saying the area is going to be equal to this length times by this length times by the sine of that angle there. So what we're going to do is we're now just going to substitute in our value. So our area is going to be 2 plus 5 root 5 divided by 4 is equal to a half times by 3 plus 2 root 5 times by c, which is the thing that we're trying to find. In this case, that is the length QR. Okay. Times by the sine of A, and the sine 30 degrees is a half, so we can just write a half there. Well, notice on both sides we've got a quarter, right? We've got a quarter here, we've got a half times a half, which is a quarter, which means that those things are going to conveniently cancel off. So we can just cancel, cancel, cancel. And so what that means is we'll be left with QR is equal to 2 plus 5 root 5 all divided through by 3 plus 2 root 5. Okay, now we can't leave it like this. We need to rationalize, and the way we rationalize is we take what's called the conjugate of the denominator. Now, if we've got 3 plus 2 root 5 on the denominator, then the conjugate is going to be 3 minus 2 root 5. And so we take that conjugate and we multiply it on the top and the bottom. We're going to multiply the numerator and denominator, beg your pardon, by 3 minus 2 root 5. Okay, so then the issue is we just got to really expand these brackets. So let's do the numerator first. We're going to have 2 times by 3, which is 6. 2 times by minus 2 root 5, which is minus 4 root 5. And we're going to have 5 root 5 times by 3, which is plus 15 root 5. And then we're going to have 5 root 5 times by minus 2 root 5, right? In other words, this thing times by this thing. Well, we just do this nice and slow. We've got 5 times by negative 2, which is minus 10. We've got root 5 times by root 5, which is 5. So negative 10 times by 5 is negative 50. Okay. All divided through by 3 times by 3 is 9. Then we're going to get 3 times by minus 2 root 5 is minus 6 root 5. But then we have 2 root 5 times by 3, which is plus 6 root 5. So those are going to cancel off. And then we're going to be left with the 2 root 5 times by minus 2 root 5. Well, 2 times by 2 is 4. And root 5 times by root 5 is 5. And 4 times by 5 is 20. Okay, so now what we can do is we can simplify all this. So we are going to have 6 minus 50, which is minus 44. And minus 4 root 5 plus 15 root 5 is going to be plus 11 root 5, all divided through by negative 11. Okay, and how are we supposed to give this answer? C plus d root 5, where c and d are integers. Well, hopefully we can recognize that everything divides through by negative 11, right? So negative 44 divided by negative 11 is 4. And 11 root 5 divided by minus 11 is minus root 5. Okay, so in the end, our answer is 4 minus root 5, which means C is equal to 4, and our D is equal to negative 1. Okay, and that's our answer. Okay, so here in question 6, what we've got is a trigonometric identity question. We want to show that the left-hand side of this identity is the same as the right-hand side. And so I think the best thing to do is always to start by saying left-hand side, in which this case is cot theta plus tan theta over sec theta. And then we try to rearrange this left-hand side until we get our right-hand side cosec theta. Now, I think generally speaking, it's not always true, but generally speaking, we want to try to convert everything through to coses and sines, okay? Because we've got here a cot, a tan, and a sec. That's a little bit complicated. We're going to convert everything through just to cos and sine. Now, cot can be written as cos over sine, and tan can be written as sine divided by cos, and sec can be written as 1 divided by cos, right? If you're not sure about sec, right, with cosec, sec, and cot, always what you're doing is you're looking at the third letter. In this case, the third letter is c, so it's 1 divided by cos. Now that we've got this, what we can do is we can try to combine these fractions here on the numerator. So the way we're going to do that is we've got to give them a common denominator. And so for the first fraction, we've got to multiply top and bottom by c, so we get c squared upon cs. For the second fraction, we multiply top and bottom by s, so we get s squared upon cs, all divided through by 1 over c. And that means that on the numerator, what we end up with is c squared plus s squared over cs, all divided through by 1 upon c. And what you should recognize is that cos squared plus sine squared is equal to 1. That's one of the basic identities. And so really what we're left with here is 1 upon cs divided by 1 upon c. And that's the same thing as 1 upon cs times by c, or c upon 1 if you prefer. And so the coses are going to cancel out. We're going to be left with 1 upon sine. And 1 upon sine is the definition of cosec. Okay, and that's our answer. We've demonstrated our identity. Okay, so here we are in part B of this question. We want to solve this particular trigonometric equation between phi is negative 540 and positive 540. Now the key word here is hence, which means we've got to use our answer for part A. And what we should recognize is that this part here can be rewritten as cosec phi by 3. So we're going to immediately change this equation to cosec phi by 3. And hopefully what you notice as well is that this thing is squared. I think that may be a mistake that lots of students will make. They'll just misread that. So cosec squared phi by 3 is equal to 2. Now we need to remember what cosec means. The key to that is always to look at the third letter, right? So 1, 2, 3, s. So cosec is 1 upon sine. So what we've got here really is 1 upon sine squared phi by 3 is equal to 2. And that means that actually if I rearrange that, then what I'm going to get is sine squared phi by 3 is equal to 1 divided by 2. And then we've got to square root both of these, both sides. So that will give me sine phi upon 3 is equal to plus or minus the square root of a half, or if you prefer, 1 upon the square root of 2. Okay. Now, if you ignore the plus and minus, what's going to happen is you're going to miss out some of your solutions. That's really important. I think that's a mistake that lots of people will make. Now, when it gets to this particular stage here, typically what I would say is replace this phi by 3 with something else. So what I will do is I'll call that theta. So I'm going to say let theta equal phi by 3. And that means that now the equation that I'm going to try to solve is sine theta equals plus or minus 1 upon root 2. Now, the reason I've done that is because personally, I think the best way to solve these kind of equations is to think about the graph of sine theta or cos theta or tan theta. Right? I know people sometimes use the quadrant formula, but what I find is that students who do that, typically they end up making mistakes. I think if you use the graph, it's a little bit more work, but you're more likely to get things right. So that's what I'm going to do. I'm going to start by drawing the graph of sine theta. So let's try to do that. Here we go. X-axis, Y-axis. Let me try to get a nice sine graph. I'm probably going to be a bit messy here, but let's try our best. Look like that. Ooh, that. Ooh, keep going. Okay. And on the negative side, that. Okay. And here we're in degrees. So I'll just label some of the key points. So this is 180. This is 360. And this is minus 180. Okay. All right. Now then, if we're trying to solve the equation sine theta is equal to positive 1 upon root 2, then what we've got to imagine is that we've got a line here, like that runs through the y value of 1 upon root 2, right, like this. And so our solutions are going to be given by the intersection points between the line and the sine curve. So it's going to be there, and here, here, and here, right? Now, we can use our calculator to find this value here, right? That would be the sine inverse of 1 upon root 2. And if we do that, then what we should get is a value of 45 degrees. Okay, now if we've done that, then we should be able to find the next value here. Right now, how can we do that? Well, we use the property of the symmetry of the graph, right? And what we should be able to see is that the distance from here to here, that's 45 degrees, must be the same thing as the distance from here to here, right? That is also going to be 45 degrees. So this coordinate is going to be 180 minus 45 degrees, which is 135 degrees. Now, if you're the kind of person who likes to just memorize formulas or things like that, then what we're learning there is that sine of theta, I'll better use x just to use a different letter, sine x is equal to sine 180 degrees minus x, or sine pi minus x if you're using radians. Okay. Well, now let's say what we want to do is we want to solve the next equation, which is sine theta is equal to minus 1 upon root 2. Well, if we do that, then we've got another line here that runs through y is equal to negative 1 upon root 2. So that would be here, negative 1 upon root 2. And so then what we're being asked to do is we're being asked to find the intersections here and here. Okay, now if we find this using our calculator, then what you should get is minus 45 degrees. And actually that should really make sense, right? Because of the properties of symmetry again, that this coordinate point here is basically similar to this coordinate point there. And then also what you should be able to see through a similar argument is that this point here, right, will be equal to minus 135 degrees for the same reason. Okay, now at this point, you could say, well, we want to find all the other subsequent values, right? So we want to find this value here, and the way we would do that is we just keep adding 360 to our existing values or subtracting 360. The reason for that is we're just moving one wave across. But in this particular question, that is unnecessary because these four values are going to be sufficient to find the values that we need within our given domain. So we have got, to clarify, you've got four solutions. Theta is equal to 45 degrees, 135 degrees, minus 45 degrees, and minus 135 degrees. And we know that our theta was equal to phi divided by 3. So phi is going to be taking each of these values and multiplying them up by 3. Okay? Okay, so if we were to multiply these out, then what would we get? Well, 45 degrees would multiply to give 135. And 135 is 405. And minus 45 is minus 135. And minus 135 is minus 405 degrees. Okay, so that should be your four values that are within the range of minus 540 and positive 540. Okay, so here we are in question 7. This is a combinations permutations type question. We're told that we want to form a team of 8 people from a group of 15 people. So part 1, find the number of different teams that can be chosen. I think probably what most people do is they'll realize that this is going to be either 15C8 or 15E8. And then for the people who are unsure, what's going to happen is they're going to end up guessing. Is it combinations or is it permutations? Now, the key thing in these questions is to ask yourself the question, does order matter or not? Right? If order matters, then we're in permutations. If order doesn't matter, then we're in combinations. Now, what does that mean in this case? Well, imagine that we are choosing this team of 8 people. Well, let's say we were to choose John, Harry, and Fred. That would be the same outcome as choosing Fred, Harry, and John, right? It's the same people, just chosen in a different order, but it doesn't matter because in the end, we would still end up with the same team, okay? So in this case, if you're choosing the team, the order in which you choose doesn't matter, and therefore we are using combinations, we are not using permutations, okay? All right, so then what we want to do is we want to take the 15C8 and we want to type that into our calculator and we should get 6435, right? 6435. Just a note, by the way, the mark scheme says that you must give the numerical answer here. You are not allowed to leave it as 15C8. You will not get your mark. Okay. Question 2, we want to find the number of different teams that can be chosen if the group of 15 people contains a family of 4 people who must be kept together. Now, I don't really like this question in slightly in the way that it's worded. I think it is a little bit ambiguous, but this is the idea, right? If you've got the family of 4 people and they've got to be kept together, then you've got 2 outcomes. One outcome is the family of 4 people is in the team, okay, like that. That's one outcome. The other outcome is they are not in the team. Right now, in both of those cases, the family is all together, right? Now, the reason I didn't like this question, as I said, is on the first time I read it, it sounded to me like that the family of 4 people must be in the team, right? They've got to be kept together. They've got to be in the team. But actually, that's not what the question says. What it says is the group of 15 people contains a family who must be kept together, right? So it's not that the team has to include the family of 4 people, right? It's rather that of the group of 15 people from which you are choosing the family, that family of 4 must stay together at all times, whether or not they're in the team or whether or not they're not in the team. So there's an element here where we need to read the question very carefully. Okay, so if they're in the team, how many ways could we do that? Well, basically, there's one way in which we can choose that family of 4 people, right? We just take them. And then what it means is that there are 11 people left to choose from because we've got 15 minus 4. We've got 11 people to choose from. And we want to choose another 4 people. So now what we're doing is we're choosing 4 people from 11 people. The number of ways that we can do that is 11 C4. So what we end up with is 1 times by 11C4. And of course, what we want is we want the numerical value of that, which would be 330. Okay, so 330. Okay, now if they're not in the team, what that means is we've got 11 people to choose from still because we can't include the 4 people from the family. But now what we want to do is we want to choose 8 people. So we're choosing 8 people from 11 people. There are 11 C8 ways of doing that. And so what we need to do again is we need to actually find the numerical value of 11 C8, which is 165. Okay. So these are the 2 alternative ways that we could end up with our solution. So we need to add these 2 together. Sometimes students ask me, why are we adding here? Well, because we've got 2 separate cases. We've either got this case or we've got this case. So if we've got this or this, then we need to add them up. So we've got 330 plus 165, which is 495 ways of reaching this possible outcome. Okay, so this is question B of our combinations permutations question. And here really what we've got to do is we've got to be able to use the formula for permutations. So let's write down what that formula is. If we've got npr, that is equal to n factorial over n minus r factorial. Okay, so that's npr. So what we've got to do is really got to use that in this particular question here. We've got to substitute out np10 and n minus 1 p9. So let's try to write that out. We're going to have n plus 9 times by np10, which can now be written as n factorial divided by n minus 10 factorial. And that's going to be equal to n squared plus 243 times by n minus 1 p9, which is the same as n minus 1 factorial, all divided through by n minus 1 minus 9 factorial. And n minus 1 minus 9 is the same thing as n minus 10 factorial. Well, hopefully what you can see is on both sides, we've got an n minus 10 factorial, right? So if we multiply both sides by n minus 10 factorial, then those are going to cancel off. Okay, well then the second property that hopefully we can exploit is if we take our n factorial here and we divide it through by n minus 1 factorial. Now, why is that? Well, for example, if I've got, let's say, 8 factorial over 7 factorial, then on the top I've got 8 times by 7 times by 6 times by 5 times by 4 times by 3 times by 2 times by 1. On the bottom I've got 7 times 6 times 5 times 4 times 3 times 2 times 1. So if I cancel top and bottom, all I'm going to be left with is 8. Right, so 8 factorial over 7 factorial is 8. In the same way, whatever 12 factorial over 11 factorial is 12. And so n factorial over n minus 1 factorial is going to be n. Okay, so what I'm going to do is I'm going to write this as n plus 9 times by n factorial over n minus 1 factorial is equal to n squared plus 243. And we just said that n factorial divided by n minus 1 factorial, right? This thing here is the same thing as n. So what we've got is n plus 9 times by n is equal to n squared plus 243. Okay, and so on the left-hand side, I'm going to get n squared plus 9n is equal to n squared plus 243. And I can chop the n squareds from both sides. So I get that and that. And so what I'm left with here is 9n is equal to 243. And so I take my 243 and I'm going to divide it through by 9. Well, I can divide through by 3, which will give me 81. And I divide it through by 3 again, which will give me 27. So n is equal to 27. Okay, guys, so here we are with question 8a. We've got a curve with this equation here, and we want to differentiate it to show that dy dx is going to be equal to this, where we've got to find out a and b. Now, the first thing to notice is that we've got one function here divided by another function. So when we've got one function divided by another function, we need to use the quotient rule. Okay, so we've got to use the quotient rule here. The way we're going to start is we're going to identify this function here. We're going to call that u, and this function here v. And so I'm going to write down u is equal to 3x minus 4 to the power of a third. And I'm going to write down that v is equal to 2x plus 1. And to use the quotient rule, I'm going to have to differentiate both of these. So I'm going to differentiate the u here. Now this is going to be a chain rule, right? So what I've got to do is I've got to take that power of a third, bring it down to the front. I get a third bracket 3x minus 4. Then I've got to subtract 1 from the power. So a third minus 1 is minus 2/3. Okay. And then lastly, I've got to differentiate inside this bracket. If I differentiate that, I get 3. So I'm going to multiply through by 3. And what you should notice is if I've got a third times by 3, then those things there are just going to cancel each other out. So I can just get rid of those. Okay, next I'm going to differentiate v. Well, if v is equal to 2x plus 1, if I differentiate that, I'm just going to get 2. Okay. Now, please notice that what I've done is I've laid out my working nice and clear. This is because it helps the examiner to see what you're doing. It also means that if you're not doing too many steps in one go, you're less likely to make a mistake. And if you do make a mistake, you're able to go back and you should be able to identify your mistake quite easily. So even though it takes a little bit of time to lay it out, I strongly recommend that you do that. Okay, next thing, quotient rule. Now, the quotient rule is v du dx minus u dv dx, so v du minus u dv, all over v squared. So now my job is just to substitute in our values. So our v is 2x plus 1. Okay. Our du dx is the 3x minus 4 to the power of minus 2/3. 3x minus 4 power of minus 2/3. Minus u, which is our 3x minus 4 to the power of a third, times by dv, which is 2. Put the 2 there. And this is all going to be divided through by v squared, which is going to be 2x plus 1 squared. Okay, now what we've got to do is we're going to have to simplify this expression. This is often where people find it most challenging. But what I want to suggest to you is you want to find this thing here, which has got the negative power. Right? We want to really get rid of that term. And the question is, well, how do we get rid of this term? Well, what we've got to do is we've got to multiply the entire numerator by 3x minus 4 to the power of 2/3. In other words, here we've got a power of minus 2/3, right? Which means that if I multiply through by the same thing to the power of positive 2/3, then what's going to happen is those are going to cancel out, right? So this thing here is going to disappear, all right? Which is what we want. So if we multiply the numerator, of course, by 3x minus 4 to the power of 2/3, well, actually, we've got to multiply the denominator by the same thing. Okay? All right, so let's try to work all of that out. So we're going to try to expand the bottom. Well, as I said, if I multiply this thing here by the 3x minus 4 to the power of 2/3, then this bit here is going to cancel off. So all I'm going to be left with is 2x plus 1. Okay, so I've got 2x plus 1. All right, then. Now if I'm going to multiply this bit here by this power, well, I've got 3x minus 4 to the power of a third times by 3x minus 4 to the power of 2/3. So what have I got to do? Well, I've got to add these powers, right? I'm going to add those powers, and that will give me 3x minus 4 to the power of a third plus 2/3, which is 1. Right? If you're not entirely sure about that, the rule is if we've got a to the power of m times by a to the power of n, that's equal to a to the power of m plus n. We add up those powers. Okay, and then lastly, on the denominator, what we're going to get is we're going to get 2x plus 1 squared times by 3x minus 4 to the power of 2/3. Then all that's left for us to do is we've got to just simplify our numerator. So here we've got 2x. This is going to be minus 6x, right? So 2x minus 6x is minus 4x. And here we've got 1. And we've got minus 2 times minus 4, which is positive 8. So 1 plus 8 is 9. Okay. And we're going to have 9 minus 4x. So 9 minus 4x, all divided through by 2x plus 1 to the power of 2, 3x minus 4 to the power of 2/3. So I'm just going to go up to the question again, just check if this is right. Well, that looks all right. So in other words, what's my a? My a is going to be negative 4, right? That's that thing. What's my b? My b is 9. So perhaps just the final part, we want to write a is equal to negative 4. We want to write b is equal to positive 9. Okay? Okay, so we're in part B now, which is to find the coordinates of the stationary point of the curve. Well, what is a stationary point? A stationary point is when the gradient is 0, which is another way of saying when y prime is equal to 0, right? That's the definition of a stationary point. But we've already found out what y prime is, or what dy dx is. It's this thing here. So really what got to do is we've got to set that equal to 0. So 0 is going to be equal to this whole thing here. But obviously that means that we're only interested in the numerator. Right, and the reason for that is if we were to multiply both sides by this denominator here, then this is going to cancel off because it's going to be multiplied by 0. Right, so we've just got 0 is equal to 9 minus 4x there, which means that x will be equal to 9 upon 4. Right, so that's the x coordinate. But we need to be a bit careful because the question says find the coordinates. Right, so we need to find the y coordinate here. So we need to substitute this x into the equation of the curve. Now, we just need to go back up a little bit. We need to remind ourselves what the equation of the curve is. It is 3x minus 4 to the power of a third over 2x plus 1. So just go back down. So y is equal to 3x minus 4 to the power of a third over 2x plus 1. Just want to, double check that I've got that right. Yeah, okay, and then we're just going to have to substitute in. So I'm going to write down again when x is equal to 9 upon 4, y is going to equal to 3 times by 9 upon 4, which is going to be 27 upon 4, minus 4 to the power of a third, all over 2 times by 9 upon 4, which is 2 plus 1. And I can simplify this, okay, so with the term here, I can combine this. The 4 here I can rewrite as 16 upon 4, and 27 upon 4 minus 16 upon 4 is 11 upon 4. We've got 11 upon 4 to the power of 1 upon 3, which is the same thing as the cube root of 11 upon 4. And on the bottom, we can combine the fractions. I can think of 1 as being equal to 2 upon 2. So 9 upon 2 plus 2 upon 2 is 11 upon 2. And if we put all this in the calculator, then I think what we should get is 0.255. And so our coordinate is going to be the 9 upon 4, 0.255. That should be our answer. Okay, so here we are in question 9, which is an arithmetic geometric progression style question. It's a little bit different, I think, from ones we've seen before. Here we've got the first 3 terms of an arithmetic progression. Our ln q to the power of 4, ln q to the power of 7. Q is positive constant. And the sum of n terms is this thing here, 4, 8, 4, 5 ln q. We want to find the value of n. Well, since we've got an arithmetic progression, what we want to do is we want to find the first term and we want to find the common difference. Now, what I would suggest you do is you want to rewrite these things here using the logarithm rules, right? So the first term, okay, that's ln q, okay? But the second term, instead of writing it as ln q to the power of 4, we can write this as 4 times by ln q, okay? And similarly, the third term is 7 times by ln q. And if that's the case, then we can say that the first term of our arithmetic progression is just ln q. And our common difference, d, is going to be, well, we can subtract any of the 2 terms, right? So we take this term, 4 ln q, minus this term, which will give us 3 ln q. We get 3 ln q there. All right, so now we've got our first term, we've got our common difference. We can substitute these in to the formula for the sum of the first n terms. And the formula for the sum of the first n terms is n upon 2 bracket 2a plus n minus 1 times by d. So what we're saying is, okay, the sum of the first n terms is 4845 ln q, and that's going to be equal to n upon 2 bracket 2a, so it's going to be 2 times by ln q, plus n minus 1 times by d, which is 3 ln q. Okay, so what we're going to have here is we're just going to have a bit of rearranging to do. Now, firstly, I hope you noticed that we've got a common factor of ln q, right? So if we divide the left-hand side by ln q, that's going to go. The right-hand side by ln q, that's going to go as well, right? So we can immediately simplify what we've got. So here on the left-hand side, we have 4845 is equal to n upon 2 bracket 2 plus 3n minus 3. Okay, and keeping it nice and slow, n upon 2, bracket, we got 3n, 2 minus 3 is minus 1. So it looks like what we're going to end up here with is a quadratic. So we're going to take our 4, 8, 4, 5, and we'll multiply it by 2 on both sides. Okay, and that's going to give us 9690. So we're going to get 9690 is equal to n times by 3n minus 1. So that's going to be 3n squared minus n. We're going to end up with a quadratic, which is 0 is equal to 3n squared minus n minus 9690. I think it's probably going to be quite a difficult quadratic to factorize in your head. So I suggest at this point, the best thing to do is either use a calculator, or if you don't have a calculator, you can use the quadratic formula. Okay, and if you do that, you're going to get a positive and a negative solution. The negative solution we're not interested in. The positive solution you get is n is equal to 57. Okay, so I think that means that we've solved our answer to part A. Okay then, so we're now in part B. Here we've got, instead of an arithmetic progression, we've got a geometric progression. The first couple of terms are p to the power of 3x, p to the power of x, and p to the power of negative x, where p is a positive integer. We want to find the nth term of this progression. Well, it's really the same thing with the previous part, right? Is we want to find the first term, and here what we want to do is we want to find the common ratio, right? It's a geometric progression, so we're not finding the common difference, because that's arithmetic. We want to find the common ratio. So how are we going to find the common ratio? Well, we take any two terms and we divide the latter term by the former term. So in this case, what we're going to do is I'm going to take this thing, p to the x, I'm going to divide it by p to the 3x. But of course, you could also do p to the minus x divided by p to the x. That would also be fine. So first term is p to the 3x. Common ratio, as I said, we can do p to the x divided by p to the 3x. And then we can use our indices rules to say this is the same thing as p to the power of minus 2x. Why is that? Well, if you remember the indices rules, if I have got a to the power of x divided by a to the power of y, I subtract the powers, I get a to the power of x minus y. So here what I've got is x minus 3x is negative 2x, right? So I've got my first term, I've got my common ratio. I want to find the nth term of this progression. Well, if I've got the nth term of a geometric progression, that is equal to a times by r to the power of n minus 1. So I just substitute in, my a is p to the power of 3x, my r is p to the power of negative 2x, and this is raised to the power of n minus 1. Well, again, what I've got to do is I've got to remember the other indices rules. One of them I need to know is if I've got a to the power of x to the power of y, then this will be equal to a to the power of x times by y. In other words, I multiply the powers. So that's going to be important here because I'm going to get negative 2x times by n minus 1. If I do that, here I'm going to get p to the power of 3x times by p to the power of minus 2x times by n is minus 2nx. And minus 2x times by minus 1 is plus 2x. Of course, here what I've got is I've got another indices rule. And this indices rule is if I've got a to the power of x times by a to the power of y, then that's equal to a to the power of x plus y. I'm adding the powers. So here what I'm going to get is p to the power of 3x plus this whole thing here, be minus 2nx plus 2x. I could write that as p to the power of 5x minus 2nx. I'm just going to check the way they wanted me to answer the question. They want it in the form a plus bn to the power of x. So I can factorize out my x to give me 5 minus 2n to the times by x. So in this case, my a is 5 and my b is negative 2. So you may want to write that as well. So a is equal to 5 and b is equal to -2. Okay, and that's that answer. Okay, here we are in part C of this question. So we have a different geometric progression here, and we're told that it's between 0 and pi/3 for theta, and we want to find the set of values for theta for which this progression has a sum to infinity. Now, really, I think the key thing here is understanding the condition for a sum to infinity. For a sum to infinity, the common ratio needs to be between -1 and +1. So what we want to do is we want to find the common ratio, and then we want to find the values of theta for which the common ratio is between -1 and +1. Okay, so first thing we've got to do is we need to actually find the common ratio. How are we going to do that? We can take two consecutive terms, and we can do the latter divided by the former. So for example, we're going to take the second term, we'll divide it by the first term. If I do that, I'm going to get 16 upon 9 cos to the power of 4, 3 theta. And I'm going to divide that through by 4 upon 3 cos to the power of 2, 3 theta. And if I cancel off, I'm going to get 16 upon 9 divided by 4/3, which is the same as timesing by 3 upon 4. I'm going to have cos to the 4 divided by cos squared is cos squared. And hopefully what you can see is that things are going to cancel off, right? Divide top and bottom by 4, divide top and bottom by 3. We're going to end up with 4/3 cos squared 3 theta. Okay, so 4/3 cos squared 3 theta. Now, remember our condition. We want this common ratio to be between -1 and +1. Well, if this is a cos squared term here, then it doesn't matter what value of theta we've got. We're always going to be positive. We are always guaranteed to be greater than or equal to 0. So we don't have to worry about the condition of being greater than -1. What we've got to worry about is being less than +1. So the thing we're really trying to solve now is we want to try to solve where 4/3 cos squared 3 theta is less than +1. Okay, and I suppose actually the range of values we're going to be having is between 0 and +1, but it's really being less than +1, which is the one that's interesting for us. Okay, so how are we going to do this? Well, first thing is whenever I'm solving trigonometric equations, I tend to do a substitution, but I think it makes it easier. I'm going to say let x equal 3 theta, so that instead what I'm trying to do is I'm trying to solve 4/3 cos squared x is less than 1. And the reason I'm going to do that is because later on I'm going to use a graph, and it's easier if I graph out cos x. Okay, so if this is the case, what I'm going to get is cos squared x needs to be less than 3/4. And so then if this is the case, I'm going to square root both sides. Well, if I square root both sides, I've got a positive and a negative solution. Now, what does that mean? It means that cos x is going to be less than root 3 upon 2, but it also means that cos x must be greater than negative root 3 upon 2. So our solution is going to be within this region, right? Cos x must be greater than negative root 3 upon 2, and it's got to be less than positive root 3 upon 2. Now, what's the best way to do this? I think really the best way to do this is with a graph. So I'm going to draw out a graph of cos x. So here's my graph, like that, okay? And if I draw cos x, which I hope to do well, it's not the best graph I've ever drawn in my life, but let's try to make it at least look reasonably presentable. Okay. So there's the graph of cos x. So here is pi by 2. This is pi. That's 3 pi by 2. This is the x-axis. Now, we want our cos x to be less than root 3 upon 2. So what I'm going to do is I'm going to draw a line that is y equals root 3 upon 2. So that's going to be that line there. Okay, so that's y equals root 3 upon 2. And we also want to be greater than minus root 3 upon 2. So I'm going to draw another line. It'll be like that, I guess. Hopefully that's good enough. And that's going to be minus root 3 upon 2. So what are we saying? We want our solution to be somewhere in this region here, right? That region there, because that's where we're going to be less than root 3 upon 2 and also greater than minus root 3 upon 2. So we're trying to find out what this region here is, right? That region, which I'll draw it, I guess, in red. That region there. Okay. All right, now then, in order to do that, what we've got to do is we've got to find the intersection points of root 3 upon 2 with the cos x graph and minus root 3 upon 2 with the cos x graph. Now, we can use a calculator to do this. If we do this, that value there is going to be pi by 6. And through symmetry, this value here is going to be 5 pi by 6. So if we're trying to find out where cos x is between minus root 3 upon 2 and positive root 3 upon 2, well, that's like saying we want x to be between 5 pi upon 6 and pi upon 6, right? So in other words, our solutions for x need to be between here and here, okay? These are not less than or equal to, they are or greater than or equal to. There is no equality here, right? Because if we're actually equal to this value, then what's going to happen is our common ratio is going to be equal to 1. If it's equal to 1, we're not going to have a sum to infinity, right? The terms will all be equal. Okay, well, I said that x is equal to 3 theta, so it's the same thing as saying 3 theta. Must be between pi by 6 and 5 pi by 6. And therefore, theta must be between 5 pi upon 18 and pi upon 18. Okay, so that would be our solution. I suppose as well, you may have to consider the case where the common ratio is 0, because common ratio is 0 means that you don't have a sum to infinity either, because all the terms would be 0. But really, this is the nub of the problem. I also noticed that on the mark scheme, I think one of these has got an equal sign there. It's like less than or equal to. I looked at the question for a little bit. I can't see a justification for that. It may be that I've misread the question a little bit, or there's some aspect that I haven't quite got there. But I'm reasonably confident that this is right. So if you've got a reason to disagree or you think I've misunderstood, I'd really welcome comments on that. You can post down below. But I hope the explanation for this is clear and it's helped you. Okay. Maybe just finally, what I will do is I'm going to post in a graph of the Desmos for the common ratio. So if I just take this here, what I'll try to do is I'm just going to post that in. Just give me 1 second. Okay, so here is the Desmos of the graph of 4/3 cos squared 3 theta, and I've drawn on the line y is equal to 1. So what I want you to see is that for all of these values here, which is between pi upon 18 all the way up to 5 pi upon 18, that this graph is less than -1, and it's also obviously greater than, it's less than +1, and it's obviously greater than -1. So hopefully you can see that so long as I'm between pi by 18 and 5 pi by 18, I would have met the condition that the common ratio is less than +1. Okay, I hope that helps. Okay, so here we are now in question 10. So we are given a function and we are asked to differentiate it. Well, the most important thing to identify is we've got one function here multiplied by another function. So when we've got the product of two functions, we need to use the product rule. So our first function here is going to be u is equal to 3x plus 1 squared. Our second function is going to be ln 3x plus 1. And so we're going to differentiate both of these. So u prime, here we've got a chain rule. So I bring the 2 down to the front and subtract 1 from the power. Then I look inside the bracket, I differentiate it, I get 3, and I multiply by 3. For v, again, I got another chain rule. So what I got to do is if I differentiate the ln, I get 1 over 3x plus 1. Then I differentiate the 3x plus 1, I get a 3, and I multiply it by 3. So I'm going to end up with that there. Now, the product rule is v du plus u dv, okay, or if you prefer vu prime plus uv prime. I say v du plus u dv because it helps me to memorize it. And so now I've got to substitute into here, so I'm going to get ln 3x plus 1 times by u prime, which is 6 3x plus 1, plus u, which is 3x plus 1 squared, times by the 3 upon 3x plus 1. So if I were to rearrange that, I've got 3 bracket 3x plus 1 all squared divided by 3x plus 1. And hopefully what you can see is that this is going to simplify. I'm going to divide top and bottom by 3x plus 1. That goes. And I'm just going to tidy this up a tiny bit. I'm going to rewrite this here as 6 bracket 3x plus 1 times by ln 3x plus 1 plus 3 bracket 3x plus 1. Okay, and that should be our answer. Okay, so now we're in part B of this question. We want to integrate this function here, but remember the key word is hence. Hence means we've got to look back to our answer to part A. So if we go back to part A, what we did is we differentiated this thing here, and we found out that that gave us this thing here. Okay, now what does that mean? Well, we can think of integration as the reverse of differentiation. So in other words, if I was to integrate this function, we would get back where we started. So I think I'm going to start by writing that. I'm going to say that the integral of 6 bracket 3x plus 1 times by the natural log of 3x plus 1 plus 3 bracket 3x plus 1 dx is going to equal to my original function, which was 3x plus 1 squared ln 3x plus 1. So let me just write that down. 3x plus 1 squared times by ln 3x plus 1. But of course, I can't forget that I've got here a constant of integration. I've got a plus c. Now then, the thing is, what I want to do is I want to find this integral here. So I want to try to rearrange this thing in such a way that I am finding that integral. Well, this thing looks very, very similar to this thing here. So let's just try to separate out our integral. So what we're going to do is we're going to say, okay, I'm going to split the integral up. So I'm going to get 6, the integral of 3x plus 1 ln 3x plus 1 dx plus 3, the integral of 3x plus 1 dx is equal to everything that's on the right-hand side. Okay, so let's just repeat. Just to explain that step, right, I've got this thing plus this thing, so I can split that up into 2 separate integrals, right? So I've got one integral here, another integral here. And the 6 and the 3, these are constants of integration, so I can just take them straight outside of the integral. Now, this thing is now what I want to find, right? That's that thing. So why don't I give it a letter? I'll just call it I for integral. This is going to be 6I plus 3 times by this whole integral here. Well, I think I can just integrate that straight up. If I integrate 3x, what I'm going to get is 3 upon 2x squared. If I integrate the 1, I'm going to get x. Okay, and that's going to be equal to bracket 3x plus 1 all squared times by the natural log of 3x plus 1 plus my constant of integration c. Then all I've got to do is just got to rearrange this so that 6i is equal to this whole thing, 3x plus 1 squared ln 3x plus 1 minus 3 bracket 3 upon 2x squared plus x. Okay, all of that plus c. And then I can divide both sides through by 6. I won't bother to rewrite that because it was quite tedious to do. I can divide through by 6 and just get rid of that thing there. Okay. All right, now I think that's the answer. I'm just going to quickly check the mark scheme, make sure that I've got that right. Okay, the mark scheme I think wants us to simplify things by the looks of it. So we can just rewrite this as a sixth, 3x plus 1 squared times by ln 3x plus 1. We would have here minus 9 upon 2x squared. So if I divide that through by 6, I would divide it by through by, I'll write that out, 9 upon 2, divide by 6x squared, minus 3 upon 6x plus c. And let's just cancel top and bottom. Sorry, I'm struggling to do things in my head today. If I divide that by 3, that becomes that becomes that. I divide top and bottom by 3, that becomes a half. So I'm left with 3 upon 4x squared. Okay, so that's 3 upon 4x squared. And this is a half x squared. Okay, and I think that should be your answer.